Assuming that we have a set of hypotheses to test, but null, everything is okay, there's no differences, there's no change, or we want to phrase that. And an alternate, there is a difference, there is a change, it increased, it decreased, whatever it is. I need a good set of data to then answer the question. Again, our data must be clean. So we have to make sure we've removed all the duplicates. We've dealt with missing or incomplete entries, inconsistencies. Somebody types out the word Pennsylvania, somebody abbreviates it PA, somebody writes Pittsburgh PGH. I can't tell you the number of times I've seen that. When you write a phone number, I know the last time you wrote a phone number, a long time ago, you put the dashes between the area code, the prefix, and the extension. You put parentheses around the area code. Different people write these fields different ways. So if you're doing a survey, make sure you've created a consistent entry format. You put the 1 before it. If you've got international country code, you put that as well. +44, plus whatever it is. Transform your data if needed. Dates and times have to be uniform. It doesn't make sense to ask if you're working about something at 9 a.m. if you're in Eastern Standard Time, but your partner is in Hawaii. Put it all in one place. It's in one spreadsheet or one SQL database. Make sure you can get a complete picture. Choose the pieces of the records that matter to your questions. If you've got 18 different fields there, but you only need 2 of them, get rid of the rest of them. Hide them. Hide the columns. Filter down by title. All sorts of options. If you need additional data from other sources, go get it. Add it in. One of the most difficult things to do is to make sure you have as complete a picture as you can use, because there's a very important acronym when dealing with data analysis. What's this stand for? This is something to beware of. If you put garbage in, you're going to get garbage out. So please make sure you have as accurate and as complete a set of data as you can use when you go to do a test on your hypotheses, whatever those are. So let's assume we've got complete, decent data. There are really 4 main types of tests that we can do. The most common we will do is called a student t-test. An interesting reason for this being called a student t-test. The gentleman who developed this idea, a man by the name of Gossett, worked for a company, and the company didn't want anybody to know he was using their data to do his analysis. Gossett worked with very small samples as opposed to very large samples. When you have large samples, you can make nice assumptions about the way you do your sampling. You have small samples, but you don't necessarily know a lot about the samples. You end up having to make some distinctions. So Gossett worked with, at one point, a sample of basically 3 items. And he still developed this idea of a test. So the company that Gossett worked for wouldn't let him publish under his own name. He had to publish it under student. Gossett worked for Guinness Brewing, So next semester, we'll go into the differences to why we use this test most. So the t-test can be done in 3 different ways. A one-sample test tests your information against some benchmark. I'm going to call this, for the moment, mu0. If I'm checking to see an average, this is a known value. If I'm checking a proportion, I'll call it pi0. If I'm checking for variation, I'll call it sigma0. But I've got some known value I'm checking against. Then we look at our hypotheses. Our hypotheses come in 3 different flavors. Either I think there's no difference, my data matches, in which case, what's my alternate hypothesis? I could say this, by the way, is a 2-tail test. Because if it's not equal, it could be high, it could be low, I don't know. Could be in either direction. I could say it's less than or equal to, in which case my alternate hypothesis is that it's bigger than. Again, since I'm only looking on one side, this will be a 1-tail. As a matter of fact, because we are looking for large values, this is a right tail. If my null hypothesis says, oh, well, it's bigger than or equal to what I was looking for, my alternate will be less than. This is also a 1-tail, and it's a left tail. Now, when Gossett was working with his samples, he said, if I've got particularly small samples, what I'm going to need to do is examine what effect the smallness has on what's going on. And it turns out that the primary effect of that smallness is to change kurtosis. Wait a minute. What was kurtosis? Felix? It looks at the tails. A high kurtosis means fat tails, a low kurtosis means no tails, really. The smaller the sample, the bigger the kurtosis. The more likely we are to have very odd, disparate data, and so we'll have bigger tails. And so what Gossett did is he designed a new distribution. The reason we call it a t-test is he created a t-distribution, and he adjusted the kurtosis based on how many things we had. And he called this the degrees of freedom. And the degrees of freedom, commonly abbreviated DF, is simply one less than the number of data points in my sample. Now this curve happens to have a shape very similar to what is called a normal distribution. But it's got thicker tails and a slightly smaller peak as a result of that increased kurtosis. What Gossett did is he said, okay, we're going to take our data. If I'm looking at averages, we're going to take our data, find its average, and determine how far off that is based on the standard deviation. But I need to account for how few things I have, so I'm going to divide the standard deviation by the square root of our number of objects. This thing down here is called the standard error. Now, if I'm looking, let's say, at a two-tail test, two tails, then I want to know if my thing is different. I need extraordinary evidence for an extraordinary claim. We said we were going to have a particular cutoff value that we called a sensitivity, this alpha thing. And we were using an alpha of 0.05 almost all the time. What Gossett said was, I want you to tell me how much of this curve is 5% of the area. And if we're out there in that 5% region, then it's really unlikely this just happened by random chance. So he figures out where the lines are so that these two pieces add up to 5%. By the way, if it's a one-tail test, then we only check one of the sides. If it's two, we use them both. 2.5% at the bottom, 2.5% at the top. Then we find where this number is on the horizontal axis. Now, I'm the first person to tell you I can do all this crap with a table, but I'm not going to do a damn bit of it on a table. I'm going to throw this data into Excel and figure out what's going on. So here is some data sets. Lecture 15 document on our Canvas page. Please go get it. This is the first data set I want to start with. What was the lecture? 15. So what we need to do is put this data into a spreadsheet as a single column. And then I can go through and figure out all of these values. I can have Excel do all the work for me. Here is my information. Please notice, filled in two numbers based on my question. If I go back and I look at that question again, the question says, is the average sales from the last 10 months equal to 500? So my benchmark for this is 500. I want to know, did we get an average of 500? I need to know a bunch of information here. If I were to do this calculation by hand, I'd need the average, the standard deviation. But those are easy. Average. It's pretty close to 500. It's not exactly 500. But is the difference from 500 important? This is what a test tells me. Am I far enough off that it means something? I need the standard deviation. It even says .s. I'm almost always going to use a standard deviation .s when I'm doing a t-test because I'm looking at samples. If I want to know how many, I just have to count them up. Count the number of data values. But I already know that that's 10 because it asked me, it told me in the actual question itself from the last 10 months. Degrees of freedom. How do I get degrees of freedom? Logan, say that louder. Right. So I take this exact number here and subtract 1. So I can now ask, hey, what's the p-value here? I want to know, did this turn out? I'm going to do this part by hand. So this calculated t-value, I wrote down the formula for the calculated t-value. Calculated t-value is the average minus the benchmark, not equals, minus the benchmark, divided by the standard deviation divided by the square root, SQRT, of how many things there are. This is going to be a negative number. Why do I know this is going to be negative? Joe?
Subtract a smaller.
My given average is 498. My benchmark is 500. I take the benchmark away, taking larger number away from smaller number. It's got to be negative. It's just fairly small, but it is a negative number. Oh, the number of things in my data set. The count. Okay. So if I go back to that picture, I need to know in this picture, is 0.429 negative 0.429? Is it far enough to the left to be in the shaded part? Is it in the unshaded part? I don't know yet. Joe, question. Oh, SQRT. So when I actually write it, it's written in square root.
Did you mentally input the benchmark?
Yes, I just typed those in. Now, if I want to know whether we are in the the part of our curve where we should say, no, this null hypothesis is not valid, I need a p-value. The p-value can be found by looking up that calculated t in our distribution. So I'm going to tell this to do a t distribution equals t. Hey, look, a whole bunch of stuff that just came up, right? And the one at the very beginning says distribution, t dot dist. But I was looking for two tails or one tails. Which tail was I looking for? Because it was equals or not equals. Is it 500 or is it different from 500? So I want a two-tail test. T dot distribution dot two-tail dot dist dot 2t. And then I need to look up, okay, two-tail distribution always uses absolute value. You'll notice that when I put that parentheses, it gives me, oh, give me the x. Well, the x shouldn't be negative, the x should be positive. So I'm going to write ABS for absolute value of this thing. Comma. Notice what it says after that. Degrees of freedom. Where did we put degrees of freedom? It's right up there at DF, isn't it? Bink. How do I know whether to keep or reject the null hypothesis? This is what we said on Thursday. Joe.
The alpha?
What about the alpha? Yes, the alpha, but what about it?
Plus the alpha.
If the P is less than the alpha, you reject. So in this case, when I hit enter, what do I get? Something smaller than 0.05? No. And that means I can't reject this information. Wait a minute. My null hypothesis. My null hypothesis was that my average is 500. The alternate hypothesis is that my average is not 500. Either I hit my benchmark or I didn't. I came up at 498. What this says is that 498 is not really all that different from 500. It's close to hell enough. Our data supports the idea that the average sales in the last 10 months are 500 units per store, units per month, or whatever we're measuring this in. Any variation from 500 is just random chance. It's just the vagaries of the capitalist system, the time of year, the variation we have just because we have. Questions? Yes, sir. The calculated T comes with our formula. It is the difference between our average and the benchmark divided by the standard error. Standard error is standard deviation divided by the square root of our count. The color coding on those boxes tells me which one is used at which symbol. That's the formula I gave on the piece of paper. Let me back out of here for a second. This one right here. Now, yes. Well, that was my hypothesis, right? Either because the question asked, I go back to the question. The question asked, is the average sales equal to 500? Well, that's my assumption. Yeah, there's no difference between the last 10 months and my assumed benchmark. I made the sales numbers I was supposed to. So what's the alternate to that? The mutually exclusive opposite is that it's not 500. Whether it's lower or higher, I don't know, but it's not 500. More questions? Now, unfortunately for us, well, fortunately for us, we have this computer. Gossett didn't. So what Gossett actually did was he wrote out all of the different chances for all sorts of different values. And that is this number right here, this critical number. If I want to know where the cutoff is, remember in my picture, I drew that vertical bar and I drew the shaded areas. If I want to know where the cutoff is, I can look that up as well. Equals T dot, this time I'm not using the distribution, I'm using the inverse of the distribution. I want to know, where do I get the 5% line? T dot INV. Now again, there are two versions, a one tail and a two tail. I'm going to use the two tail. And now it asks me, oh, what's the alpha you're looking at? What's the probability you're looking for? I know where alpha is. Alpha's right here. What's your degrees of freedom? Degrees of freedom are right here. Now, since we chose 5%, that 0.05, that was just put in manually by default. In other words, if I did that calculated T, I need a number that's either bigger than 2.26 or smaller than negative 2.26 to get the cutoffs. My number was in the middle, isn't it? So if I go back to the picture, this cutoff line is at 2.26 and negative 2.26, and our value is negative 0.4 something. It's here. The white unshaded region in this picture is the, well, that could have happened randomly. It's only, hey, something weird is going on if we're an outlier. So Gossett's test, the t-test, tells us, hey, this data is an outlier. Something weird is happening. And in that case, our null hypothesis goes out the window. Now, I did this manually. Let's try this again, a slightly different way. I'm just going to copy this data again and get rid of all of this junk. That's why I made a copy. I didn't want to lose what I had done, but now I have just the data. I can ask Excel to do this. Under my data tab, under my data analysis options, there's a bunch of stuff there, right? But when I open this up, what do you see at the bottom of this? In that little box? I see a problem. What does everything say up there? All of those t-tests. They say 2, right? They don't say 1, not any of them. Ah, crap. I got a lot of tests up here. None of them are automatic one sample tests. Well, that means that's the way I have to do this. I have to do this in a calculations manual. Doesn't that just suck? But those tests included a bunch of things that said 2 samples. So what changes? If I start talking about 2 samples instead of 1. Well, now I'm doing a comparison. Instead of just asking, did I meet my number? Did I get 500? I can say, look at the first store and look at the second store. Is one store doing significantly better than the other? Now, maybe those 2 stores have something in common. Maybe they don't. So I have another breakdown. I did say this test could be done in a number of different ways. So I'm going to make an assumption here. If I have independent samples, what does independent mean in this case? Well, it means the 2 data sets are separate. They may or may not have anything in common, but they certainly aren't in direct connection with each other. I really like the store 1 and store 2 idea here. But I could also think of it as 2 separate days of the week. I want to know about sales on Mondays versus sales on Tuesdays. I can do that. I want to know about drug prices in Texas versus Colorado. I want to know about a particular drug. I look at insulin prices. Are insulin prices different in Colorado versus Texas? Now, there are some assumptions made about the population here. And the assumption I am going to use the most is that what we have are equal variances. If I want to avoid this assumption, I'm going to need to make some changes to the way I calculate things. There is a way to do that. I'll save that for next semester in the stats course. What this does is it does a similar sort of calculation, but instead of looking at our sample versus a benchmark, it looks at the difference between our 2 samples and compares it to 0. unless we think there should be a particular difference. If I was comparing drug prices in Texas with drug prices in California, hey, which place has a higher cost of living? Texas or California? Yeah, last time I checked, California had a much higher cost of living than Texas did. So if I was making a comparison between drug prices in Texas and California, I might have to take into account there should be a difference proportionate to the cost of living. So instead of comparing our data to an arbitrary benchmark, our null hypothesis now looks at the difference between those two pieces and asks, is it 0 or is it not 0? Once again, that's a two-tail. There'll be a left tail and a right tail version if you have greater than or less than in your alternate hypothesis. You can swap out any of those rows. Fortunately for me, these are the tests Excel will do automatically. Here is my next data set. 2 stores, not 1. Please notice store A is the same data we were using in the previous example. So grab this data, throw it into Excel. Make 1 column for store A and 1 column for store B. I'm sorry? Is there a formula so it goes directly into? No, I have to put it in. I can take it. I can do transpose. That'll switch rows to columns. When you go to paste, instead of hitting Command V, hit Command Shift V. There's an option there that says transpose. That'll make it 2 columns. Then you just cut the second part and put it on the bottom. You also, I don't actually think you need to leave it in a single column, but I do that by default. When I go to paste a set of data, Command Shift V, wait a minute, Command Control V. Sometimes it's easier to right click, paste special. And when I paste special, there are all sorts of options. One of them usually includes transpose. If not, paste it in as a row and then leave it as a row so that column store A will be a row and store B will be a row. You can do that way too. There's no requirement to be in columns. You can do rows. Now this time there's no benchmark because I'm comparing store A to store B. I'm going to say, I don't think there's a difference. My null hypothesis, H0, the average for store 1 is the same as the average for store 2. My alternate hypothesis there is a difference now. Again, it could be one is lower, it could be higher, I don't know. I'm just saying there is a difference. I don't know what the average is for group 1, I don't know what the average is for group 2. But I'm assuming for the moment that I want to know only is there a significant difference here? Could this difference have happened by random chance, or must it be caused by something? I don't know what that cause is. The store clerk at store B smiles more. The store clerk at store B is strapped. I don't know. Take what kind of store is this? I want to run a t-test. I want to run a 2-sample t-test. Please notice, as well as distributions, what's the bottom thing that shows up when I start typing t dot? It literally says test. T dot test. And now it asks me, is this, where's data set 1? Where's data set 2? So I'm going to put in data set 1, comma, data set 2, comma. Okay, notice it brought up a checkbox. There are 2 options here. Based on my hypotheses, am I doing a 1-tail or a 2-tail test? I'm doing a 2-tail. It's either the same or it's different. I don't know whether it's low or high. I haven't specified. So this is a 2-tail test. That means I put a 2 for this option. Comma. Now here's where I can find my workaround. I said we were going to assume something about the variations in my population. What was I going to assume about my variance? Wrote it down. I was going to assume that the variances were equal and that the samples were independent. That's one of the options here. It says in the middle option right there, 2-sample equal variance. And then it uses a word that I have never seen used anywhere else. If the variance is the same, it's homoskedastic. I've never heard that term outside of this command. I don't care, just call it equal variances and we're good. So I put another 2. If I didn't want to say I knew the variances were equal, I could pick option 3. That makes changes to the way we calculate the degrees of freedom. It makes changes to the way we calculate our t-value. And it makes changes to the way our p-value comes up. When I hit enter here, I get a p-value. How do I know whether or not to reject or keep my null hypothesis? Joe?
It's if it's lower than alpha, it's higher.
Exactly. I'm going to get a number if that number is smaller than our alpha. Our sensitivity by default is 0.05. If whatever comes out of hitting enter here is smaller than 0.05, choose the alternate hypothesis. If whatever comes out of here is bigger than or equal to 0.05, choose the null. What do I get? I cannot reject my null hypothesis. There is a variation between these two stores, but whatever store variation there is random chance. There's no statistically significant difference between these two stores. That's actually a key statement. Statistically significant doesn't always mean practically significant. I would like to point out to you an issue that came up at Seton Hill, I think a dozen years ago. We did a study on campus about harassment issues. And we found that there were a statistically significant number of sexual harassment cases on campus. And I mean the p-value was 0.00001. That's really statistically significant. That's a lot smaller than 0.05, right? I then went and stuck my hand in the air because I'm a little bit of statistics. I went, wait a minute. Out of how many possible cases did we have a positive result? Because we were testing a proportion. Well, it turned out we had 3 reported sexual assaults, one of which there was someone found guilty. 33% is really significant. 1 out of 3 in the past 5 years. Practically significant? Absolutely. The persons who were involved, that was absolutely significant. In the grand scheme of the 7,500 students that had been on campus in the time, statistically, yes. Practically, less so. Less, but not. So there's a difference between practical significance and statistically significant. Questions? I did say that we found this under the data thing, right? So let's go back to that data tab for a second. If you click on data up here in the upper ribbon, all the way over on the right is that data analysis button. Click that. And here we see again our 3 t-tests, 3 possible choices. And the one we are looking at is the middle one, t-test assuming equal variances. I'm going to click on that. And when I click OK, it's going to give me a checkbox of lists of things. Where's the stuff for variable 1? Well, variable 1 is store A. Please notice that when I highlight, I do not include the label, or I can include the label. I'm going to choose to include the label this time. Then I need to put in the variable 2 data. So I click down here, and I do the same thing for store B. By the way, there's a checkbox. I put the labels in the top row or the top first column if your stuff is in rows instead. Check labels. Remember I said we might assume that there is some clear difference? If I think that one of these stores is, $100 different than the other, or $1,000 different than the other, I can put what I think that difference is in the third box here. I'm going to leave that blank because I was asking if these are equal. If I think there is a difference, I put that number here. I'm going to ask it to put all the answers that it gives me into a new sheet. That's why this middle thing is checked. That gives me a new worksheet. It's going to put the answers in a new page. All I'm going to hit is OK. All right, what the hell is all of this? These are my answers. But this did more than just the two-tailed t-test. You do see that 0.645 up here, right? The answer we got from the previous one, P was 0.645, yes? If you round that number, that's 0.645, isn't it? And it even says that is the p-value for a two-tail test. But I didn't tell it what the hypotheses were. I didn't tell it what's the null hypothesis, what's the alternate hypothesis. So it doesn't know if I'm doing a two-tail t-test or a one-tail t-test. It has no idea. So it gives me both p-values so that I can decide which one I need, the one-tail or the two-tail. You'll notice the degrees of freedom. There were 10 things in group 1, or 10 things in group 2, took away 1 from each, the degrees of freedom. It goes so far as to give me the t-value, the calculated t-value that I wrote up the formula for. It's calling it t-stat instead of t-calc. But it gives me the p-value. Because I gave it 0.05 as our sensitivity, our alpha. Questions? Okay, so back on the data page, under data analysis, do you not have that? Okay, then what you need to do is to go to Tools and go to Excel add-ins up. And when you click on Excel add-ins, one of the things you can check on is the analysis toolpack. Make sure that's checked. That's where the data analysis stuff is. You should also check the solver because it helps with some of the other things. Once those are both checked, you should have access to the same thing. You might have to quit and re-enter Excel to make sure they start up. I don't know for sure. Okay, so you got the data analysis block here. Click on that and find me the t-tests. Okay, t-test assuming equal variance to sample. Make sure you've got the first data in the first one and the second data in the second one. And then check that new worksheet ply. And that is what's going to give us that whole separate page. I can do these manually. The same way I did the test for the other one, the calculation is slightly different. Doing the actual degrees of freedom and the other pieces, there's a little more to the standard error here. The formula is a lot uglier. I don't like doing this by hand. As a matter of fact, I don't like doing this so much by hand that I found out I don't even need Excel to do it. Those are built in here as well. You see this stat button right here? I can edit lists of data. If I edit and type in all the data I'm working with, if I have the two stores, I can do store A in list 1 and store B in list 2. I can then do a test. Hey, look. Number 4 there says 2 sample t-test. Number 2 just says t-test. That's the 1 sample version. It'll do it automatically on the calculator, in spite of the fact it won't do it automatically in Excel. But once I get here, I can say, oh, my data is in list 1 and list 2. Am I doing a two-tail or a low or a high one tail. I pool the variances if I think they have equal variances. That's what this pooled statement means. And then I hit calculate, and it'll give me the same information that Excel gave me. So it is possible to double check all of these separately. I know you are much more probably happy working in Excel than you are working in a graphing calculator. I've been using one of those calculators since the mid-90s. I'm pretty facile with them. If I think I have different variances, as opposed to assuming equal variances, then I can use the unequal variance checkbox test instead of the equal variance one. The output looks almost exactly the same. Questions? So we'd assumed independent samples. Our data sets are unrelated. But what if my data sets are related? What if I have you do an exercise program, and then I give you a particular pre-workout, have you do the exercise program again, right? Do I see different results? I'm measuring blood sugar in people who have non-insulin dependent diabetes. So I take your blood sugar every day for a month, bleeding into the little machine every morning when you wake up, and then I give you a brand new drug, a variation on GLP-1 drug, Mounjaro, Ozempic. Those were originally designed as diabetic drugs. The blood sugar drugs, they just happen to have appetite effects. Here, try this new drug. Let's see if it changes your blood sugar. You take it for 30 days, and then we do another 30-day test on your blood sugar. It's you both times, isn't it? It's you before and after. So those samples are related. We're going to call those paired samples. I want to measure, did my sales numbers go up because of the new advertising campaign? So I look at the sales numbers before the advertising campaign and the sales numbers after the advertising campaign. A new type of packaging on my object. I changed the color of the can for my energy drink. Did sales go up or down? I might also be able to say I have the same group of people look at two different products. Do you prefer version 1 of this item or version 2 of this item? Give me a scale on how much or how little you like it. Everything else we do becomes the same. But this pairing of samples means that I'm actually thinking of a direct connection between these numbers. The first number with the first number, the second number with the second number, the fourth number with the fourth number, the 10th number with the 10th number. So here, I have a spending promotion. Look at my sales data before and after a particular promotion goes out. Maybe in week 1, I looked at my sales, and on Friday or Saturday, I sent out an email to all of my customers and said, hey, next week, come in and get $3 off. And this is what happened. So let's run a t-test. Take this data, put it into a spreadsheet, Let's run a t-test. There's our promotion sales data. Now I can do this directly in a one line command. I can say, hey, I want a t-test. So I say equals t.test. Array 1, comma, array 2, comma, type. Am I doing a one-tail or a two-tail test? Maybe this is the hard way to go about this. Let's do it the other way. What's the other way? I can do it in the data analysis tab. So let's find that data analysis tab again. And this time, when I pull up the test, t-test paired to sample. There it is right there. Paired to sample. So again, it'll ask me, where's variable 1? There's variable 1. Where's variable 2? There's variable 2. I included the labels. And I want all my information in a new slide, a new page. You could ask it to put the information right here. You don't have to put it on a new page. You could say, I want you to put this information right there. By saying output range. If you check that output range box, wherever your cursor is, whatever cell you indicate, it'll put it to the right and down from there. I like putting them in new pages so I don't screw anything up on this page, but that's my personal choice. I click OK. It gave me all the information. So here's my question. What was the question I asked on the piece of paper? The question that is in the lecture document. What does it actually say? Did spending go up? So I need you to answer that question. Did spending go up? Yes or no? In order for me to answer that question, I didn't even do this in advance. This was done with me. I need to have a null hypothesis and alternate hypothesis if I'm testing it. What is my null hypothesis for this problem? What is my alternate hypothesis for this problem? What's my null hypothesis? Felix. There's no difference. Spending did not go up. Which means my alternate hypothesis is spending did go up. Okay. Alpha. We put it in when we did the test. What's our alpha value here? Same alpha we've used every time. What's our alpha value? 0.05. So now I need to know which p-value I should be using. So now I need you to answer the question. One tail or two tails? Ron, say that louder. Because the alternate says went up. That's one side, isn't it? That's one tail. So I need to look at the p-value for the one tail test. Is that smaller than 0.05? I need a quick lesson in how to read in Excel. What the hell does that E thing mean? Joe. You're just going to answer the question. And so the answer is that smaller than 0.05 or not?
No.
Except for the fact that that E is in there. You look at that, you're going 6.3. 6.3 is big, right? That means exponent. That E means exponent. We have to move the decimal place because that's an E -6. That's times 10 to the -6. So take that decimal place and move it 6 spots to the left. In other words, that number is 0.000006. Is that smaller than 0.05? That's a lot smaller than 0.05. That exponent, that E, is a critically important piece of this piece of value. If I don't know what that number means, I'm royally screwed at that point. But I could tell another way. Even if I don't want to read that p-value, I can compare the t that was calculated against the t that is provided. See the t value for a one tail? It's 1.8. Even if we assume it's the negative 1.8, our t value is negative 8.57. That's way out there, isn't it? That's way out there. That means we're in those shaded regions. The shaded regions are the reject. So now I can answer the question. Did spending go up? Do I reject my null hypothesis or do I keep it? That's what's going to tell me. I reject the null hypothesis, which means as far as I can tell, this data supports the idea that spending went up. I could do a two-tail test. Please notice that the p-value for a two-tail test is bigger because it split the area into two pieces, right? There's more. So I want to check either of those. But since I was asked, did it go up? I'm really doing a one-directional test. You should check when doing a t-test that we have a sample, that we know how many things we have. By the way, the larger our sample, the smaller the weird kurtosis effects are. So when we have lots of data, this will be roughly normal. I'll talk about that version next semester. It's a z-test rather than a t-test. Make sure you choose the right kind of t-test. Are your samples related or not? Are they paired? Do you have equal variance or not? If you're not sure or you're not told about the variances, you probably want to assume they're not equal. And then make sure you are careful in interpreting what the p-value means, which really means before you even start doing any calculations, the first thing you should write down before doing anything are those hypotheses every time. So that you know whether you're doing a 1 or a 2, you know whether you're doing a paired or an unpaired, you know whether you're doing a 1 sample or a 2 sample. Extraordinary claims require extraordinary evidence. That t-stat being so far out there means it is very, very unlikely that the difference between these two things was caused by random happenstance. There's something going on here. You may not know what it is, but spending went up after we did this advertising. I can't cause and effect. I can't tell you what each individual person thought. I can't tell you what they thought individually, but I can say as a group, they decided, I'm going to go spend more money this time. There are other kinds of tests we can do, especially when I'm looking at more breakdowns. If I'm just looking at means or proportions, I'm going to do a T or a Z. But there's more, and that's what we will talk about on Thursday. I will see you all then.